uh, and it's Dario Poletti from ACTD Singapore. Hi, Dario. Uh, and he will be talking about giant spin current rectification. Dario, the stage is yours.
Hi, thank you, BJ. Thank you, all the organizers, for this opportunity. Thank you for the free speakers as well for the very nice talks. Can you hear me well? You see the screen properly? Everything's
Yes,
okay?
Dario. Yes,
Okay,
yes.
fantastic. Thank you. So I would like to talk to you about rectification today. And well, Gabriele just now did some introductions to local master equations, which, as he predicted, I'm going to use and discuss now. And here is a list of some of the papers we did in the recent years on this topic. First of all, I would like to thank the group and the collaborators I worked with on this particular topic. I have other collaborators, but these are the ones that I'll think more deeply and carefully about this issue of current rectification. Okay, and the work I'm talking about today, so the idea is I will give you an introduction on spin and heat current rectification in general, and then I will dive into this giant spin current rectification in this particular model where you have an XXZ chain with interaction all over and some magnetic fields in different directions that together with the negative differential conductance will help us to have a very strong rectifications. And the people here are those who helped on this particular work. Okay, so rectifiers, we are, I guess, all familiar with the diodes and electrical current diodes since the work in the 30s on copper oxides. And we have systems which, when you put the bias in one direction, you can have a strong current. And when you put the bias in the opposite direction, you have a very, very weak current. Okay. And these things have been, this is the typical characteristic curve that you see for electrical currents, IV curve. But interestingly, they've also been studied for heat current rectifiers. And these are some of the works in these directions. I think the first ones was in 2006 by Chang and others. And the most recent that I know about is just a 2 months old in a collaboration with Jazot and Capisi. Giorgio is the first author of this paper here on the archive that came out in January. Okay, so how do you characterize when a rectifier is good? Well, we have different figures of merit. One is rectification, which here I define as the ratio of the forward versus reverse current with a minus sign because the current will be in the opposite direction. Or we can look at the contrast, which basically is the ratio between the sum of the currents divided by the difference of the currents. And just to have an idea how these things work, the rectification would be 1 when there is no rectification, and the contrast will be 0 in the case because JF equals to minus JR. And for a perfect diode, the rectification will go basically to infinity, and the contrast will go to 1. Okay, so what I'm going to do and discuss in the next of the time that I've been allocated is to talk about the quantum system between two buffs. And in one scenario, we'll call it forward bias, which is very arbitrary. We put a buff 1 on one side, buff 2 on the other side. And then we will swap these buffs and call this scenario reverse bias. And we look how the current is different and how to have strong current differences. Okay, so now that I've set the stage, there are some questions. What are the minimum ingredients, for example, to have rectification? And the first very critical ingredient you need to have is broken reflection symmetry. And while this symmetry can be broken in the system, in the buffs, or even the coupling between the system and the buffs, but somehow we need to break the symmetry. The other thing that you need to be able to generate is a nonlinear response. So a nonlinear response, basically you have a current J, which depends on 2 parameters in the buff. Let's say, for example, temperature or other potentials. And let's say you can write this as a Taylor series. What you want, you would like to have some terms, Cn or even, that contribute to the current, because if you only have the odd ones, or for example the first one, then the expression is obviously antisymmetric and you have no rectification. Okay, so how to get these things? And I think to me, there were three works by Segal, Dvir Segal herself alone, and also with some of the people of her group in 2008, 2009, that discuss some sufficient conditions in order to have rectifications. And for example, different density of states in the baths, or different particle statistic in one bath compared to the other, or maybe baths which have different statistics, for example, spin baths connected to bosonic systems that would also generate, would allow the emergence of rectification. And even suppose the baths are the same, what you can do, you can have like nonlinear terms or non-quadratic terms in the Hamiltonian, and that will also help you to have rectification. So all of these things can be thought of having some nonlinearity somewhere. And the nonlinearities can be in the effective description of the spins, because a spin, you can think of it as a strongly anharmonic harmonic oscillator, or you can think of that there are some nonlinearities in the baths which end up giving a very different density of states. And so here I mentioned some of the works. There is work of Achal Poikayasta on where he was looking at bosonic system with anharmonic terms, for example. Okay, so I think if we talk about heat rectification, two of the works that really changed the path of the field, in my understanding, is the works in 2002 and 2004 by Terrane, Pirar, Casati, and Li Wang and Casati. And in these works, what they study is classical nonlinear chains, and with different nonlinearities in the two paths. So let's take segmented chains. And the key thing, the key mechanism for this, which is actually critically important also for what I'm going to discuss later on for the quantum system, is to look at the power spectrum in each half of the chain when the system is not coupled, and how it depends on the temperature. And depending on the nonlinearity in the systems, you could have, for example, for the red portion, that at low temperatures for T left less than TR, only high frequency response because of the particular nonlinear structure that you have on the left-hand side. But as the temperature increases, you can have more and more low frequency response, which overlaps with the power spectrum of the right-hand side. And so when there is an overlap between the power spectra of the left-hand side and right-hand side, that's when you can have a very good currents. And when there is no overlap, you will have very little currents. And this is what really helps to get very strong rectification. And all of this discussion about this rectification and phononics in general can be found in this review of 2012 by Lee, Hangi, Lee, and others. Okay, so now that we think about nonlinearity, and since I want to talk about quantum systems, the first thing that came to our mind was to say, okay, let's map nonlinearity to strongly interacting systems. This will be the path that we'll try to follow to generate very strong rectifications. Obviously, before we started to work on this, there were some nice works in the field, both in classical and quantum systems. I would just like to name 3 quantum systems and 1 classical one here. I already mentioned the work by Archak in 2016 with for bosonic systems with non-quadratic terms, and then quartic terms, basically. Then there works also by Arake and others in 2009 on spin chains, where the baths were quite different because of different magnetic fields in the baths. And then there was this nice work where the authors managed to achieve optimal rectifications. This is rectification of infinite rectification of contrast equal to 1. A comment on these works, the first 2, as was common in many works in this field, the rectification is not particularly strong. As you can see here, the values maybe 0.4, or here the values maybe 1.5, and so on and so forth. These other works, they managed to achieve optimal rectification, but I don't think that is scalable to a system of large system sizes, and it would not work for large system sizes. So this is something that motivated us to try to find very strong rectifications. Now, I would like to also to mention a very recent work by our chairman here on classical systems, but it's also quite insightful. The system is fully quadratic, but they are able to find a rectification by having like different a temperature gradient in the baths. And it's also so what I'm trying to say is also that there is still a lot of ideas and still a lot of things that are coming up in this field. And there are many other works by Schaller, Pereira, Landi, and so on and so forth. Okay, so let me try to say about how we tried one of the paths, and actually we described two paths that we chose and we followed to try to find a very strong rectification. Okay, so the models that we will be using most of the time, it's an XXZ model with a tunneling and anisotropy. And then there is with or without anisotropy. I may refer when I talk to this anisotropy sometimes also as interactions, because well, after Jordan-Wigner transformation, this term gives nearest neighbor interaction in a spinless Fermi model. Now, as anticipated by Gabriele before, I'm going to use to describe transport here some local master equations, and we will not consider issues about thermodynamic validity of this or the consequences or interpretations of these equations. And one thing that I would like to stress is that the results that we're going to show depend on the energy structure of the bulk Hamiltonian, so they're not significantly dependent on the particular bath that we use. And when later on, for one example, I may talk about heat currents, we will not be using these master equations. Okay, so the idea of this master equation, though, I should stress a little bit. On one side, you have something that tries to raise the spin, okay, and lower the spins with a different rate. This is given that this 1 plus mu1 and 1 minus mu1, this is for the first side. And for the last side, it will also have some jump operators try to raise or lower the spin with the coefficient 1 minus mu and 1 plus mu l. Okay, so the first thing that we try to do, and this was a collaboration with my postdoc Vinita and then Pereira, Beninte, and Casati, was to look at an XXZ chain coupled to an XX chain, okay, with a small coupling gem. So here on one side, we had a bath that was trying to impose a spin all pointing down, and the other side pointing like towards the infinite temperature state. And doing so, just to explain a little bit better, suppose that the two chains are not coupled. The result that we will have one half of the chain in one bias, which is in the infinite temperature state, and the other one is fully pointing down. And this is what we call forward bias. And then what we call the reverse bias, we'll have this side, the left-hand side, where the interaction is present, that is all pointing down, and the other side that is infinite temperature state. Okay, once we've done so, we looked at the system, and first we looked at the small chains, and already we could see that for 8 or 10 spins, if the anisotropy or interaction is large enough, we will have very, very strong contrast, basically perfect rectification. And as we increase the system size, I will not show the analysis here. There shows that there is a critical value, okay, of delta over J, which is equal to 1 plus square root of 2, where the system goes from the reverse bias, okay, the system in reverse bias goes from being diffusive to being insulating, while the forward bias is always diffusive. And in this case, so the forward bias has some current, the reverse bias is an insulator, and so the system becomes a perfect rectifier. Just to give you an idea how this works, what happens is that for large delta over J, the spectral response is gapped in reverse bias, but not in forward bias. And let me try to give you a pictorial intuition of this. Let's go back to this picture that I had before. This is the reverse bias, when on the left-hand side, all the spin will pointing down, and the right-hand side, where the infinite temperature state. And now, you know, we don't think about the bath, just prepare the state like this. And now from not coupling it, we couple it. And the only thing that can happen is that there is some excitation that produces here at the edge. Now the question is this excitation gap will be localized or can it spread out? And what turns out that in the reverse bias, if the anisotropy is large enough, this excitation is kept, okay? The excitation on the left-hand side are of the order of delta. On the right-hand side are of the order of J. So if delta is large enough, and in particular if it's larger than 1 possible for 2J, then there is a gap that forms and the excitation will be gapped, and hence it will be exponentially localized. If it's exponentially localized, it cannot propagate and reach the buffs, and so there will be no current. In forward bias instead, on the left-hand side, we have the infinite temperature state. And on the right-hand side, we have this state that point down. So in this case, there will always be some lower excitations. And so close to zero energy. And in thermodynamic limit, it really exactly can approach very close to zero energy. And so this excitation can propagate, it can reach the buff. And so in forward bias, you actually can have currents. So you see that some of the ideas that generated and discussed before for the classical system kind of come back here. This is very nice. We can get a perfect rectifier, but the rectification drops significantly. Okay, and everything is significant a drop when you go from infinite to finite, but it drops significantly when on the left hand side you don't drive exactly to this state O pointing down. Okay, and for example, if you use thermal buffs, and there the simulation was done with global master equations, we get a rectification about 200, which is still not small. But we were wondering whether it is possible to find another mechanism that can help to have very strong rectification, and maybe is more stable against the details of couplings to the buff. And this what we thought of using is another effect that comes into play in interacting systems, which is negative differential conductance. Okay, this was first discovered by Isaac in the 50s and so on and so forth. What is negative differential conductance? Basically, you increase the voltage, but the current decreases. Okay, and this is a very important effect in all the electronics that we use. So what did we do here? Okay, and we took some of the works that I done Benenti and others. Actually, there were these two very nice works in 2009 with Rossini, Snidaric, Casati, Benenti, and where they studied an XZ chain with large anisotropy, and they try to have a buff that is similar to what we did just now, is trying to impose a polarization or pointing down on one side and pointing up on the other side. And as you change this value of mu, you change the bias, and so the driving between the left and the right hand side. What they observed, this is current versus driving, current versus mu, for different system sizes, is that the current will go increase as you increase mu, but then it will tend to increase, and then eventually for mu equals to 1, the system becomes an insulator. Okay, and the mechanism actually behind this is that as you increase the driving, you form some ferromagnetic domains at the edges here. I don't know if you can see my mouse. You can see some ferromagnetic domains here at the edges, and so the system becomes an insulator. Okay, so we have this effect there. We know that it happens when you have strong driving, and we were wondering how we can use it to have strong rectification. Okay, so this was the new mechanism that we're trying. And what we did, okay, we took our XZ chain with an isotropy delta. We took these buffs that try to set up these polarizations at the edges, less of strong bias. And we added local magnetic fields. So this is the term that we added. And to have a better view of all the possible combinations, we looked at locally, the field could be either plus H or minus H. And if you have L spins, we have 2 to the L possible configurations. And since we're not studying very large system, we can consider all of them. And so we consider all the configurations, and we try to see whether anything interesting happens. So this is what we try to do. And let's start very small, baby steps with just four spins. Okay, we looked at the current, as you can see, versus strength of the magnetic field divided by the anisotropy. And I don't know if you can see very well the gray curves, gray lines, but you can see definitely the red dotted line and the blue dashed line. These two correspond to actually two reflection symmetric configurations of the magnetic fields. And we see that for a good portion of values of H, they correspond to actually the largest current and the lowest current. So this is already telling us, hey, maybe we can use this for rectification, because these two are two reflection symmetric configurations, and they correspond to the largest current and the lowest current. And we can also see that the values of the currents are very, very, very different. Okay, and so we can expect a significant rectification, because on the left-hand side, this is a log scale. Okay, so it's a semi-log plot. Okay, so we did the same for 6 spins and 8 spins, and we did observe something very consistent, that for large portions of the values of H for delta, these two configurations corresponded to the configuration with large current and the smallest currents. And so we will expect a very strong current. And we look at the ratio of the currents, this can be extremely large. Okay. Actually, the effect improves as you increase the system size. So here we were looking at all the possible configurations. Now, if we take one configurations and we all the configurations and we look at their rectifications, okay, then actually it turns out that if we consider rectification, the setup in which half of the magnetic fields are pointing up and half are pointing down corresponds to the scenario with the largest rectification overall. Okay, because here, for example, some of these currents, they had a very large current, but the reverse also had large current. So the rectification for these scenarios may not be very large. And so overall, this actually corresponds to the scenario with the largest currents. And this is consistent even if we increase the system size. Whether we go from 4 to 6 to 8, this scenario corresponds to the larger rectification. Let me just clarify one thing. Rectification less than 1 doesn't mean that there is no rectification. Actually means there is rectification. It's just that it's going in the opposite direction of what we expect, or what we call forward bias and reverse bias. But if you look at the absolute values, also for these other scenarios, they're always smaller than the configuration that we chose with half spins up and half spins down. So that is still the one with a stronger effect. And as you can see, for just 8 system sizes, we can have rectification of the order of 10 to the 8. Okay, it's not perfect, but it's extremely large. Okay, we can also look at the effect of different disorder or the strength of the magnetic fields. If these magnetic fields are small, okay, we do have rectification. It's not very large. Maybe we can get a value of 10. And what is interesting here, though, is that we do see the rectification close to delta equals to 1, which is where the system has a quantum phase transition, and where if you're familiar with clean XXZ chain in this strong bias, the system goes from ballistic to insulated. So there is some strong signature of the underlying transport properties of the XXZ chain that come here, but because of the presence of this magnetic field is enhanced, and we have a strong rectification. Not I wouldn't say strong, rectification of 10 for small value of H. Now, as we increase the magnetic field, we can have a very, very strong rectification, and the underlying structure of the clean HZ chain becomes less important, but we still see this very strong effects. So continuing, the question obviously is, what is the mechanism, okay, that generates such an effect? Okay, so the interplay between the buffs and the interactions, as was studied by Benitez and Dario and so on, tends to give this state, which is half of the chain points down and half of the chain points up. Okay, this was discovered before, and just to give you an idea, this is what we showed here. Okay, these strong domains, okay, which turn the system into an insulator. Okay, let me go back. So now, if we add a magnetic field with a pointing up in half and pointing down the other half of the chain, this is something that lowers the energy of the system. While if I put the fields in the opposite direction, will increase the energy in the field. Okay, this actually affects the stability of the steady state, this particular state, and whether it allows it to be the eventual steady state of the system, or whether this steady state will decay into something else, and then it will actually have currents. Let me try to give you a better intuition, going back to a very small system with just four spins. Okay, so if you have h equals to 0, the states are half of the spin, half of the spin down, or vice versa. The state half of the spin down, half of the spin up. They're both here. They're both a high energy state, okay, and they're degenerate. Now, as we increase h, what happens is that one of the states, in particular up, up, down, down, goes further away from all the other possible states, while the state down, down, up, up will go across and will go through some of the crossings with the other states in the system. And this is what makes this state unstable. It's going to mix it with other ones, and because of that, it's going to decay, and it cannot stay. It cannot be the steady state. While with these other systems, which is liked by the buffs, and it's becoming an eigenstate of the Hamiltonian, can become the steady state of the system. And it's exactly at these other crossings that if we look at the forward bias current, we see two major peaks in the currents. While if you look at the reverse bias, the current doesn't see anything, because there is no other crossing that this state will go across. And if we look at the rectification, then we will see exactly at these points of the maximum, we see these peaks in the rectification. Now, what happens for larger systems? For larger systems, the initial point here is the same. If we look at the configuration with half spin ups or half spin down, or its reflection symmetry configuration, half spin down, half spin up, they will both be the high energy states, eigenstates of the Hamiltonian. But then what happens to this state that will come down, will go through a much thicker band with a more dense band of states, okay? And we'll go through many more of the crossings. And that's why it's going to be still unstable. And this is why the effect also happens for large system sizes, and actually will happen more, it will be even more prominent, because there are many more of the crossings. It will be much more unstable. Now, we cannot simulate these systems for very large system sizes. Why? Although we can use tensor networks, and we're quite familiar with these methods, and these methods can, for certain scenarios, describe very, very large systems. For this particular configuration of negative differential conductance and with very small currents, and so on and so forth, actually, there are some very small relaxation gaps, and the matrices you're playing with are very ill-conditioned. So it's very, very difficult to go through long times. But to get an insight for large system sizes, we can still play around and try to look at, since the main physics that's happening, it's in the bulk, it's in the Hamiltonian of the system. We can look at these two states, the half spin ups and half spin down, or the opposite, and look at their IPR with the eigenstates of the Hamiltonian. To do this, it's easy also to compare to like system size of 16, for example. This is easy to simulate. And in this case, we can see that, what is the IPR? IPR is the overlap of the state that we're considering with the eigenstates and to the modulus 4. So this is equal to 1 when psi is an eigenstate, and it is going to be a very small number when psi has overlap with the other states. And actually, if it's completely delocalized and it's a large overlap with many eigenstates of the Hamiltonian, the IPR will tend to 0. So if I plot 1 minus IPR, okay, when it's delocalized, it will go close to 1. And when it is localized, it will go down to 0. And this is what we observe. The state, half of the chain up and half of the chain down, as you increase h, as a very large IPR, meaning it's basically becoming an eigenstate of the Hamiltonian. So it's a state that satisfies both the dissipators, and the eigenstates are Hamiltonian. So it's close as possible, as you know, to this. The steady state is a very good approximation of the steady state of the system, and it's a state that has no current. But if I look at the other scenario in the opposite direction, with half a spin down and the other half of the spin up, then I see that there is this whole region, which is where it crosses the band, okay, in which the IPR is very small, and the states are this state is not, it's definitely not an eigenstate of the Hamiltonian. It's actually spread over mean, is highly unstable, and eventually you end up with something that has a current. Okay, so we are very sure that this system is this effect will be present also for larger and larger system sizes. And this is related to what I was telling you before, that as we increase the system size, this band becomes more dense. And here, this is all of these peaks are due to many more levels in these bands. Okay. And for a small enough J, this band has a width is 2 delta. So at least for H up to 2 delta, we can have a very, very strong rectifications. Beyond this, both states are eigenstates, and we can go back to see here. For a H large enough, both states will become eigenstates of the Hamiltonian, and so they will have both weak current for both directions. But it turns out that the current for the reverse pi is still smaller, so we can still have some rectification, but it will not be a very strong rectification, not compared to what we can get in this region here in the middle. And nicely enough, when we increase the system sizes, we can have a very, very strong rectifications in these regions. Okay, as we've shown this with this example, even with just 8 spins. Okay, so now I get to the conclusions. We have studied the interplay between negative differential conductance and the presence of a Taylor magnetic field, and this has given us a new mechanism to generate very strong rectifications. And the response in one direction is significantly different, and this is because in one way the magnetic fields favor the formation of these ferromagnetic domains, and so favor the presence of something that is not conducting. While in the other direction, the magnetic fields go against the formation of these ferromagnetic domains, and so the system can still the insulating solution is unstable, and you will have current, and this results in giant spin current rectification. So in the future, what can we do? We can look at heat currents, of course. We already have some preliminary results. Things are quite interesting. So hopefully in a matter of a few weeks, we'll be able to give you some updates on this, on the archives at least. And then also on non-ideal scenarios, we also did some works in this direction where we try to put some integrability breaking perturbations in the different parts of the chains or the presence of other baths. But there is something that I would like to stress, and it's related to the fact of the development of numerical methods. As I mentioned, especially in the second half of the talk and towards the last, we were able to see very clearly results for maybe 8, 10 spin chains in these very, very difficult regimes. But going beyond it is particularly demanding. So I would like to spend the last few minutes just to highlight some things about numerical methods very briefly. Okay, so from my understanding, or maybe my bias, the way I've been formed and the type of groups I had the chance to work with like my previous supervisor, Corina Collate, and so on. The study of transporting many-body open quantum systems, basically the best approach, especially in 1D that I know, is the use of tensor networks. Okay, and as you have probably seen some amazing results, right? It's Nidarich and others, most very much driven by him. Close to infinite temperature, you can study systems even up to 400 spins, and this is pretty amazing, pretty interesting. But this is not the regimes we were looking at. We were looking at regimes very far from infinite temperature, and where maybe number conservation can be useful. So in this case, what could be in avenue is to rely on symmetries in the systems, and this is a route that we're trying to follow. And recently we looked at we implemented a matrix product states code for closed and open systems, which tries to detect whether there are symmetries and use them to speed up the codes. But there is another thing that is also quite important, is how do you model the buffs, and it's also related to what Gabriele was saying before. And model the buff for many body systems that will be studied with tensor networks. And this is, I think, it's an interesting route. So suppose we are going to use tensor networks, and you don't have to, but there will be a number of groups that are doing this because they have a lot of potential, especially in 1D for many body systems. There's been a number of proposals, and some are very interesting, and I would like just to mention a few. For example, Prosen and Darich in 2009 came up with this idea of applying some local linear buffs on the two sides or a portion of the systems, and that is very good to simulate high temperatures. Then in 2010, 2014, but also later on some evolutions in 2015 adding thermofield, there was this works on stuff-to-chain mappings. In 2010, was, I think, mostly driven by Martin Peña's group, Susan Huelga, and so on. And there this is ideal also for matrix product states, because when you have a system you couple to a buff, you buff of many harmonic oscillators, you map this many harmonic oscillator in a semi-infinite chain. And this allows you to study the systems up to a certain amount of time. And there has been work also to use to translate Redfield master equations for matrix product states. And this was work done also in collaboration with one of the organizers here, Joseph Tina. And it's also quite interesting. He was able to push study many body systems with Redfield to 20 or more spin, which was not done before. And very recent last year, and one poster I want to highlight, and Gabriel also highlighted, work by Pukayasta, which is related to collisional model or refreshing the buffs, which allows to study very large many body systems. So what I would like to say is that there is a lot of interesting things in physics, but there's also there is a need for development of numerical methods that will allow us to explore such systems. Okay, with this I conclude. I thank my collaborators, as I did before as well, particularly the three that were related on the project on giant rectifications with these diagrammatic fields that I discussed. Thank you very much. Of course, I would like to thank
Dario, for this exciting talk.
Yes, sorry, I forgot to thank the support for the Ministry of Education and the National Supercomputing Center as well. We run a lot of our simulations. Thank you, Vijay, sorry.
No problem. Thank you, Dario. All right, we have some time for questions. So I could see Archak has raised his hand. Archak, go ahead.
Hi, Dario, and thanks a lot for highlighting the poster. Yes. So I was a bit confused in between that. So when you talk about this half of the chain being up and half of the chain being down, is that the initial state or the steady state?
Okay, is the steady okay. In the insulating case, the steady state is going to be very close to that. Now I would like to understand whether that can be the steady state. And so one way I can do that is I prepare the system in that configuration, I couple it to the bus, and I see whether it's stable or not. Okay, so depending on what I was discussing, it can be one or the other. In the insulating regime, that would be the steady state, or a very good approximation of the steady state. Is this clear? Because just to continue on this issue of stability or not, it may be very difficult to find the steady state, but it may be easier to see whether a certain configuration is stable once you couple it to the bus.
Okay.
That it takes a lot less time to simulate. So then we can also do that. Okay, we actually do both.
I see. And another very general question about rectification is that, I mean, in rectification is like used in daily life for rectifying AC voltages. I mean, has there been any work on these kind of things?
So to rectify what did you say?
Like AC voltage, right? I mean, that's
okay. I didn't look into AC voltages yet. Various reasons are again related to the method. Once you have AC, basically you have periodic driving, and then you need to be careful the master equation you're using and how you're using them. So far we focused on the DC. There is definitely interest in AC. Let me give you an example. One of the first works I was talking about before, and also actually ours are coming up. Give me a second. Faster if I do. Okay. So this, do you see my screen? Okay.
Yeah.
This work here, where we have perfect rectification, or for example, other works where, like our works, where we see this strong effect. Now we know that there is a gap, okay, and this helps the formation of this. Now, what happens if you drive close to that energy? Okay, how is going to mess up the system? Okay, and actually, can we use this to find some very nice, interesting effects? So this is definitely a research direction I'm very interested in. I think there is a lot of interesting things there.
Okay, thanks. Thanks a lot.
Yeah, I could see Jay has raised his hand. Jay, go ahead.
Thank you for the nice talk. You showed that if you attach your system to a different heat bath, then you can induce some current in your system through the system. My question is, instead of attaching your system to the heat bath, suppose that you apply some kind of time-dependent boundary field. So your system is isolated, but you apply some time-dependent, any kind of operated the two different boundaries. Then in this way, can you induce some current through the system?
Okay. So I would like to first thank you very much for your question, and also thank you for your talk. It was very nice. It's another research direction I like to follow. One clarification first. Most of the buffs that I showed just now, I wouldn't call them heat buffs. And I mentioned some results on heat currents, but it's not the main ones I talked about. As also Gabriele described before, we need to be careful when talking about local master equations, how in Limler form and their relations to heat buffs. Now, once you have driving, okay, that is okay. This is very interesting question. First of all, I think things will be quite different depending on the properties of the system you're looking at, whether it's, for example, integrable or not. And in this case, and here for integrable, I mean that there is a large enough number of quasi-local constant quantities, bit in the spirit of many works of Prost and also Jean-Sebastian Coe, Mossel, and these kind of people. What is difficult though is to show that there is a clear steady state, and there's been some work in these directions on I forgot. Saito did some works in this direction, and I think something can happen, but I'm not very sure exactly what it would be, because usually these drivings are constant across. And if we relate to also the previous questions, there has been a nice work by Picorn and Prosen, where they had periodically driving, and that they did see emergence of long-range correlations. So at least in that scenario, long-range correlation can appear. So maybe it can also appear in these scenarios where everything is unitary. I can send you the reference if you're interested.
Yeah. Okay.
Thank you. So maybe, thank you. So
Sorry,
maybe Dario, I'll ask one question. Oh, go. Yeah, Judith. No, go ahead.
Sorry,
go ahead. I think we are running out of time.
I did not have a raise hand button here, so I'm
Oh,
sorry
okay, go
for
ahead.
this.
No, go ahead. Go ahead.
Maybe a quick clarification, Dario. So in your talk, you had these sort of gray lines which corresponded to different configurations
Yes.
in the rectification, and there were some with negative, but those were also quite large. What
Yes.
configurations do those correspond to? I think
this one, sir.
yeah, exactly.
You're referring to this, right?
Yes, absolutely. And if I look at the negative rectification ratio that you have here, it's smaller than the maximum one for sure, but they're still quite large, right?
Yes.
And this also corresponds to rectification, as you said. But what are these configurations?
They are quite similar to the half up and half down. They're like, let's say, almost half, but some other perturbation somewhere in the middle. Or, yes.
So there are some sort of excited states from these half-half configurations with one spin.
Yes, some small changes from those. Exactly.
Okay, I see. Thank you.
You're welcome.
Okay, I think we are almost out of time because the poster session is going to start in about 2 minutes. So I think let us thank Dario once again for this wonderful talk, and also all the 3 speakers for this session. So the poster session will begin shortly, and I hope you all can again join there, and we'll also see you tomorrow.